The next problem that we'll study, which has a greedy algorithm, is again a job scheduling problem, and a slightly different version of what we have seen in the past. Okay, so the setting here again is that we have one shared resource, right? The single resource, which we said is either, let's say, a processor or a classroom. Okay, and we have many jobs, right? Many requests that want to use this resource. Okay, so maybe many tasks that need to be executed on the processor. But now the setting is different in that each job now does not have a fixed start and a finish time. Okay, so it's not necessarily that the job has to start at a given time, but so it's flexible in that when it can be scheduled. Okay, so each job will have a length, a duration, which is an estimate of the time that it needs to, that it will take to complete. But it's flexible in where it needs to be scheduled. Okay, so because of this, there is no notion of an overlap of two input jobs because they can be moved around, scheduled at different times. But right, so we'd like to schedule all the jobs, okay, because we can pick their start times, different start times. We'd like to schedule all the jobs on the resource such that we minimize a certain cost function or maximize a certain benefit function. Right? So we'll see what this cost function is soon. Okay, so yeah, so the setting here is that each job has two attributes. The first is the length, right? How long the job executes. So also its duration, which will denote by Li. So I is the index of the job. The ith job has length Li. The second attribute is known as the weight of the job, okay, or the priority of a job. Okay, this is modeling scenarios where the jobs have different importance. Right? So let's say if a UG student wants to schedule a task on that big machine, or a PhD student has to schedule a job, maybe for some reason the PhD student gets a higher priority, right? Or a faculty wants to schedule a job, the job of that particular faculty would get a higher priority than others. Okay, so this occurs in real life. So this weight is an attribute that can model these differing priorities. Okay, so again, we'll denote as Wi the weight of the ith job. Okay, so yeah. So as an example, let's say we have three jobs, and the length of the first job is 1 time unit. The length of the second job is 2 time units, and the length of the third job is 3 time units. Okay. Now we could have different ways of scheduling this. So let's say schedule 1. The first way we schedule this is we first do job 1, then we do job 2, then we do job 3. Okay. So we first do job 1, which has length 1. Then we do job 2, which has length 2. And then we do job 3, which has length 3. Okay, this is one way of scheduling the jobs. Let's look at another schedule where we first schedule, let's say we schedule job 2, then we schedule job 1, and then we schedule job 3. Okay, so in this case, we'll simply have the first job that is scheduled has duration 2. Then the next job, L1 is scheduled. Job 1 which is scheduled, which has duration L1 equals 1. And finally, job 3 is scheduled, which has duration 3 time units. Okay. So we'll introduce some terminology that will be needed to solve the problem. So we'll define the completion time of a job. Okay. So completion time of a job I in a particular schedule. Right, in a particular schedule. So given a schedule, we can define this completion time of a job I is simply, so informally, I'll just say is the sum of all the job lengths scheduled before I, scheduled before a job I, right? Sum of all the job lengths scheduled before job I plus the length of the job I. Okay. So it's simply saying at what time does the job I get completed in a given schedule. Okay. So for example, here in this schedule 1, if I would say completion time of job 1, it's simply 1, right? Because after the first time unit, job 1 is over here, job 1 has finished completion, right? It has completed its execution. What time does the second job finish? Well, it's simply 1 plus 2, right? So the completion time of job 2 is simply 1 plus 2, which is 3. And the completion time of job 3 here, right, at this time interval, job 3 is also finished. So that is simply 1 plus 2 plus 3, which is 6. Right? Okay. Similarly here, the completion time of job 2 is 2. The completion time of job 1 is 3. And the completion time of job 3 is 6. Okay, so I hope this is clear. What we define as a completion time of a particular job in a given schedule, right? You change the schedule and the jobs will have different completion times. Okay. Another term that we'll use in this problem is known as the weighted completion times. Okay. And as you guess, it is adding the weights, the priorities to these completion times. So given a scheduling, so let's maybe look at this particular scheduling. The weighted completion time of this is simply weighted completion time. So the weight of job 1 times its completion time. So this C1 I'm using to denote the completion time of job 1, okay, which was 1 in this case. So weighted completion time of this schedule is W1C1 plus W2C2 plus W3C3. Okay. So for each job, you take its completion time and you multiply it with the priority, with the weight of that job. Okay. So if we look at this schedule 1, what would be its weighted completion time for schedule 1? It's simply weight of job 1. Well, I haven't defined the weights of the jobs. So let's say I put some weights for the jobs. Let's say job 1 has weight 3, job 2 has weight 2, and job 3 has weight 1. Okay. So the same thing here. This is the second job's weight is 2. The first job is weight is 1. And the last job, first job is weight is 3. And the last job's weight is 1. Okay. So job 1 has the highest weight. So it is of the highest priority. Next comes job 2, and finally is job 3 in terms of the priorities. Okay. So supposing we schedule the jobs like this. Okay, then what is the weighted completion time of this schedule? Okay, we are computing this weighted completion time for a given schedule. For schedule 1, it is W1, so that's 3 times completion time of 1, which is 1. Right, in schedule 1, job 1 completes at time 1. Plus W2, which is 2 times C2, right? And completion time of job 2 in schedule 1 is 3. And finally, W3C3, so weight W3 is 1, right? And completion time of job 3 is 6, right? So 1 times 6, okay? This is 3 plus 6, right? 15. Okay, so this is the weighted completion time of schedule 1. Okay, what about for schedule 2? Can you compute the weighted scheduling time, weighted completion time, sorry, of schedule 2? Well, here the second job finishes at time 2, which has weight 2. Job 1 finishes at time 3, and it has weight 3. So 3 times, so the weight times the completion time, which is 3, right? Job 2 finishes at time 3. And finally, the last job 3 has weight 1, and it completes at time 6. Okay. So for this schedule, the weighted completion time is 4, 9, 6. Right? That's 19. All right. So given these two schedules, which one would you pick? Right? Which of these two would you say would be a better way to schedule the jobs, given these weights and their completion times? Okay, so one thing we observe is that, well, intuitively, you would like to have a scheduling which puts the higher priority jobs first, right? That's why they have this notion of a priority, that you'd like to schedule them first. So if you see that in a given schedule, right, in a given schedule like this, as the later jobs, jobs that occur later in the schedule will have higher completion times naturally, right? The jobs that occur earlier in the schedule would have lower completion times, right? So if you think about having the higher priority jobs scheduled initially, that would translate to having these having a lower weighted completion time, right? When in this term here, if the completion time is low and the if let's say the weight W1 is very high, and if its completion time is also high, that means it's scheduled later on. Okay, then this entire sum the value would increase, right? The contribution of this term would increase if W1 is high and C1 is also high. That is, if it is scheduled much later, right? As opposed to if it is scheduled earlier, right? If job one is scheduled earlier, then the term C1 would be low, and you would have maybe a high priority multiplied by some low term here. C1 would be low, and that would in some way lower the value of this term. Okay. So in some sense, we could say that we would maybe like to reduce the value of this weighted completion time. Okay. Schedules which result in high weighted completion times are not really desirable, and the ones that give us low weighted completion times, that is desirable. Okay, because those are going to put the high priority jobs at first. Okay, so now we are ready to define our problem formula. So the input to our problem is the n jobs that need to be scheduled. And it's a job I has weight Wi, right? And it has length Li. The output that we are looking for is a scheduling, right? Essentially a permutation of these n jobs. So a scheduling of the jobs that minimizes the weighted completion time. Okay. So you want a schedule which minimizes this weighted completion time. Okay, so this is this objective function that we talked about earlier. The weighted completion time is the function that we'd like to minimize. Okay, so right, so given n jobs, how do we go about finding the scheduling which has the least weighted completion time? Okay, you see that each scheduling might have a different weighted completion time, and each scheduling is basically a permutation of the n jobs, right? Different ways of arranging them in a sequence, right? So if you have n jobs, we have n factorial permutations, right? So n factorial possible schedulings, right? We have n factorial different possible schedulings. So if we have to do this naively, right, a naive algorithm will basically will look at all possible schedulings, right? For each scheduling, it will compute its weighted completion time and pick the one which has the least, right? So it's clearly correct, but this is this naive algorithm. The runtime, right? So the runtime of this naive algorithm is n factorial. Okay, it's worse than exponential, right? It's yeah. it's not something that we can work with in practical cases. Okay, so this won't work. This won't do. We'd like to do better. Definitely do polynomial time and the fastest possible maybe. Okay, so how do we go about it? So as we suggested, since this is a greedy lecture on greedy algorithms, there should be a greedy way to solve this. Okay, so how do we figure out that?